Every day we see technology continue to rapidly evolve. Therefore, keeping pace with technology will be critical to winning the war on crime. We have a great presentation, and I wish if I had a band, I'd ask for a drum roll, please. Oh, thank you. Thank you. On that note, Forensic Technology is proud to unveil the very latest innovation in automated ballistics technology. And here to do it are two of our best. Michelle Paradis, Forensic Technology Canada. Michelle is the IBIS product manager and works in Forensic Technology's marketing department. With more than a decade of software engineering experience, he leads the company's vision on software development for the IBIS Trax 3D family of products. Serge Levesque is a PhD with Forensic Technology. He's a scientist within Forensic Technology's research and prototype group. His works focus on the development of new 3D sensor technologies. His PhD is in laser spectroscopy. He has also practiced in the fields of medical imaging and artificial intelligence applied to quality control. This presentation will be a little different than the others in that there will be no question and answer period immediately following it here, because we would like to invite you back to the actual technology where they'll be happy to answer and demonstrate the answers to any of your questions. Gentlemen.
Good afternoon. IBIS started its journey more than 20 years ago. It is the world's most advanced ballistic identification solution. This technology has helped law enforcement experts to see more, link more, and solve more firearm-related crimes. The automated comparison of bullets or cartridge cases across large networks of collaborating partners has revolutionized the field of firearm forensics. IBIS was limited by the technology available at the time, such as camera resolution, automated controls, and processing power. Nevertheless, this first generation started us on the right path of effective, large-scale automated ballistic identification. Our partnership with our worldwide user base and experts has contributed to the continued success and growth of IBIS, and in the mid-1990s, new technologies enabled the development of the Trax systems. Better capabilities and increased performance revitalized IBIS networks and boosted their effectiveness. The high-resolution images are an advantage during the correlation review process, with more details to help find potential matches. Automation provides consistency and better quality images, including new types of images and the introduction of 3D topography. 3D has opened new possibilities. IBIS Trax 3D, which was that version, remains an effective solution in more than 65 countries, but there's always room for improvement. And FT continues to invest heavily in research and development, and our hard work of the past few years has resulted in remarkable advances in the area of 3D. And this is what Serge is going to talk to you about. These 3D innovations will be integrated in the upcoming release of IBIS Trax HD 3D, the latest generation of IBIS technology. They include high-definition 3D capture that is accurate to the micrometer level. They include all new 3D correlation algorithms that give us a leap in correlation performance beyond the already successful 2D correlation. And they include exceptional 3D viewing tools that bring the important surface markings to life. So this new version will include other improvements, such as new breech face sidelight correlation, which we will talk about a bit later in the presentation, bullet shape capture and viewing, polygonal bullet correlation, as well as many other improvements to the viewing tools, such as high-resolution display, the use of special 3D topography images, and new options to help review collation results. So all these other enhancements and others I didn't mention will be in this version, but this short presentation focuses on the high-definition 3D of cartridge cases. High-definition 3D for cartridge cases represents our most significant technological breakthrough in recent years. And Serge Levesque will explain the constraints and challenges of this new technology and how they were overcome. Serge?
Thank you, Michel. Okay, so technological breakthrough. When we started this project, sorry, I think I will turn this one down a little bit. When we started this project, we needed to have some objective to achieve, to calculate at the end if we achieve well in the overall. First of all, we want to ensure to maintain correlation performance over growing IBIS database size. IBIS database are growing every year because they're getting older. 20 years is old for a database, especially if you've been feeding it with hundreds or thousands of cases year after year after year. Another reason, an important reason, I think almost every speaker talked about that today, the fact that criminality went globalized over 20 last year. So it might be reasonable 20 years ago to correlate criminal database on a regional level. Now it's more necessary to do it on a country or continental level. Second objective is to increase crime fighting effectiveness with accurate and timely information. DNA entered in everyone's mind in the last 2 decades with very high accuracy for criminal investigation. It raised the bar for all other techniques. At the same time, information technology went into our everyday life. Now, within the palm of our hand, we have access to the whole internet easily. So everyone takes for granted to have accurate and timely information involving for crime solving. Finally, in some jurisdictions, the ballistic evidence are not owned by the lab when they have it. It's owned by other actor of the judiciary system, and you have to maximize the information you take from those evidence while you have it at lab. So all those three things led to the solution of trying to capture high-definition 3D image from the cartridges. It will surely maximize information collected at the time we have the ballistic evidence under hand. We've seen from the past experience with bullets that 3D along with 2D correlation helped a lot or make a gigantic step forward for correlation performances, and we hope to have the same kind of effect with cartridges. And finally, 3D information opens the door for very effective lighting, visualization tools that will help to have that timely information given to the police investigator. So once we decide to go 3D, we had to find the right technology to achieve that. It might look like an open field when we started, but we had two very important constraints to live with. First, maintain image backward compatibility. This is a ring light image from a brass tracks. It contains two important marks for correlation, the firing pin impression and the breech face impression. And today, in various IBIS databases around the world, there might be millions of those images, patiently acquired by hundreds or thousands of firearm examiners or acquisition technicians. This is a very valuable asset we cannot just get rid of. So the new sensor for 3D will and must yield some 2D image to correlate with those ones. This is a very nice 2D image taken from a known match of this cartridge. However, the optical setup, the lighting setup for this image is so different than the other one that it's impossible to compare those two images. Unfortunately, most of the 3D sensors in the market, including confocal microscopy, holography, or white light interferometry, will give this kind of 2D images. The best thing we need, so I thought I pressed the laser. What we need to do is to capture as much as possible the exact same kind of image. So now the match is more really observable by everyone in the room. Second constraint, reuse as much as possible existing hardware. This is a brass tracks. So we've deployed about a few hundred of them around the world, mainly in the 5 past years. It wouldn't be fair to say that today this is obsolete. No, the new brass tracks is exactly the same as the previous one seen from the outside. However, this one is high definition 3D capable, as this one isn't. So there might be something different somewhere. Inside the box, we have here access to the very heart of the brass track system, which is not very different from the IBIS heritage system. A motorized variable zoom microscope with a megapixel CCD camera and a ring light. In the new version, we use the exact same hardware. Same microscope, same camera, same ring light. What we add is that simple hardware here, an armed structure with light-emitting diodes, LEDs, that will, in succession, illuminate the cartridge underneath the microscope. And that's the only hardware we add in the system to get the full HD3D image. So how is that possible, to get such high-definition 3D with that simple hardware? By the method called stereo photometry, not to be confused with stereo vision. Stereo vision is the way human beings see in 3D with the use of 2 eyes, or motion picture produce the 3D movies we have since a few years. They use 2 cameras for that. It's not very useful for microscopy. Instead, we'll use the different LEDs I just talked to you about to light the cartridge in succession. So this little animation here will show the different lighting of the LEDs. And as the animation go on, you have a better and better understanding of the structure of the surface of the cartridge. At the end of the animation, we almost see the full thing in 3D. So that's how photostereometry works. It's just a mathematical formalization of that intuitive process that went inside our brain. However, it's easier said than done. There were some few constraints we had to go around to achieve that. First of all was to develop a proper model for light reflection on the surface. If you go over internet and ask about stereophotometry, you'll find a lot of application with this kind of object. Statues made of marble, clay, plaster, or other things that all share the same kind of light reflection, a very linear and easy way that light reflects on the object. It opens the door for a lot of mathematical simplification on the process and acceleration of the computation. However, I've been working in forensic for 8 years now. I've never seen a cartridge made of marble. They're more of the time they're made of nickel, brass, chrome, or other metal, and you can easily see that the light reflection on this surface is very different as this one. You need another physical model to explain that. In fact, you need a full nonlinear model, and tackling that in front as we did, and we think we're the first one and still the only one in the world to have done that, you can say goodbye to all the good simplification the linear model gave, and it's a little bit more complicated. Furthermore, if you look at those deers, they are yellowish or brass color, but in some region they're very white, and we lose totally all information about the surface on those areas. That's because the camera used by the photograph, as well as the camera we have in the brass racks, doesn't have enough dynamic range to capture the full range of light intensity reflected on those objects. So that led to the second challenge, was to develop a high dynamic range imaging. So let's pretend you take a walk somewhere in Europe and you see a nice little tower on your way. Unfortunately, you want to take a photo, but the sun is in back of the tower with a few clouds. So you say, okay, I have a new trendy camera. I can't find a setting to get a good photo out of it. But there's no way to get it because of the limited dynamic range of the camera. However, on each of these photographs, you have nice information. Here, nice contrast on the clouds. Here, the color of the sky and clouds is quite correct. And the rest of the flowers are quite good at this point. So if you take the better part of all the photographs and put that together into a single photograph, that's what you get, much more close to the human experience of taking a walk in Paris. What we develop is quite similar than that. It's also a high dynamic range image, but the goal was not to satisfy the human eye, but to satisfy the nonlinear model I taught you just before. So it was to give accurate information to the photometric model, and we turned the camera into a megapixel photometric device capable of sensing between almost 200,000 different shades of gray. Other challenge we found, and this one was more surprising, and it was frankly the most difficult we overcome, is to handle multiple reflection. A spent cartridge case has, when it's a center fire, a huge depression in the center of a shiny material. And when you put lights into that, it acts as a resonator. So with this vase as an illustration, the photograph probably had an overhead flash on its camera, and we can clearly see two specular highlights where the angle of the vase was just the right one to reflect the light back to the camera. But what about those pairs of specular highlights? It's doubtful that the photograph had side light flashes on his camera. It's more probably caused by multiple reflection inside the vase and then back to the camera. And you have even higher multiple reflection like this one, a single spot, which is a little bit on the right side of the vase, probably from 5, 6, or 7 reflection before it reached the camera. For us, it's not a big deal because we have a priori knowledge of what a vase is. We see that curvature here, and that's enough information for us to reconstruct mentally what is the structure of this image. But for a mathematical model, as evolved as it is, when you have only 1 pixel accuracy at each time, you need to make sure that the information you give to the model is coherent with the fact that it's accounted for only 1 reflection. So we had a big module of filtering of the data that goes into the model to make sure that it is coherent with a single reflection model. Finally, if you put all that together, the nonlinear model, the filtering of the information, high dynamic range imaging, you find out that you need to have sufficient computing power. This method was first proposed in the early 1980s. If you remember, at that time, it was the glorious day of the VIC-20 and Commodore 64 computer. So if we compare a computer to a plow, that would be what it looked like at that time. So certainly not enough power to resolve even the linear model I thought at the first time. But As time goes, the computer got more and more powerful, and the speed of flowing was increased, and you can do larger fields and do more complicated image processing. But still, it is not enough to get our megapixel problem with the nonlinear stereo photometry. What we needed is the latest version of computer with as multiple core or multiple plow shades in our example, and this permit to do it in a parallel manner so we get it timely enough for practical uses. But it's more difficult to do than say. We need a lot of computer science, not mathematician, but real computer science to split that nonlinear model into multiple core of a computer. So once you get everything all together, so back to the information we had, that series of different lighting on the cartridges, and the regular ring light on the other side, you end up with this 3D image. This image is what we show it as an elevation map. The brightest the pixel sits higher to the neighboring, and the darker it is, that means the pixel sits lower on the surface than the neighboring pixels. This is the raw information of the 3D structure of the surface without any sort of interpretation. It's a very powerful tool for image comparison. Very few examiners have seen that so far. It's quite new, but the few that did work with that, they like it very much. However, since it contains all the useful information on the 3D surface of the cartridge, we can use that to feed to a rendering, engine that will simulate what it looked like on a microscope using, again, physical interaction of light and object. This image is designed to be very familiar to firearm examiner. So it has the color of brass, a shiny look like a metal, but has some feature that you cannot have on a microscope. The bottom of the firing pin here sits 500 microns lower than the breech face, but they are both well into focus at the same time. You cannot do that with real optics. The specular highlights here give the shiny aspect of metal, but it's been smoothened, so you still have access to the information in that region, which is, again, not possible in real life. Finally, some words about correlation. That was our first goal. In an attempt to measure the correlation performance of the system, one needs to patiently acquire a lot of pairs, of known matching pairs of cartridges. We acquired a little bit more than 450 of those. That means more than 900 cartridges captured with the system. And we had two metrics, first position. So if either the firing pin or a breech face comparison ranking got the first position, we call it a success for first position metric. If it's within the top 10, then it's a top 10 success. With only 2D information like we have today, the results are not that bad. Yeah, 70, oh, sorry, I missed the punch. 70% for first position and 85% for top 10. If we consider only 3D data, the new data that we acquired with the system, then we cut by 2 the gap between the 2D performances and the sought after 100% performance. If we combine everything together, then we are almost to 94% for combined top 10 performance for that 1K database. So there was a belief when I entered at Forensic that there were some part of the known matching that could not be matched because they don't look the same. And at that time, the first estimation I was given was 10% or 15%. but that have to be reviewed if it really exists to less than 5%, but we are already at 94% of success with the combined metric. But as I said earlier, 1K database or 1,000 exhibit database is not the metric which we have to measure the success of coloration so far, nowadays, because databases are growing and growing. However, acquiring 50,000 cartridges is a long process, but we can simulate that by using all the non-matching score that we had for the slide before. That means almost 1 million scores of non-matching cartridge case that we had from that research. That's a lot of data that is fun to have some statistical analysis on, and that's what we did. So if we apply that statistical model to the 2D data only, we see that the system is quite robust after all, because going from 1,000 exhibit to 50,000 exhibit, we only lost about 20% of top 10 success, going from 85% to 55%. However, if we consider only 3D data, we see that 3D data is already much robust. The fast decay for the mid-sized database is almost disappeared, and we end up about 70% success rate for very large database. And there's still some complementarity between the 2D and the 3D, and that decrease in the mid-sized database is almost disappeared, and we end up a little bit more than 75% of correlation success for very large database. So back to my first goal, we can say that correlation performance on large database using 2D and 3D is much comparable to what we observe today with only 2D data on small 1,000 exhibit database. Now back to Michel that will conclude this presentation with other aspect of the new product launching today.
So, I hope you were impressed with the numbers that Serge was talking about. So it's clear that the addition of 3D correlation data, correlation of 3D data provides benefits, especially over larger databases. But where 3D technology truly shines is in visual comparisons. Let's start with the primary area. Although the markings can be seen in the 2D images, this is a match, actually, of two sister cartridge cases. The 3D topography clearly reveals the physical impressions. Did you see that? 2D, 3D, okay? And visual 3D modeling by the computer helps the human brain to more easily interpret those markings that are there. And we have a variety of controls that are available to optimize the visual comparison and help reach a conclusion. 3D viewing is based on high-definition surface topography and 2D images together. Of course, these are static images that I presented here, and that they can't fully demonstrate the visual quality when the models are moving and you see the reflection of the light moving on the computer screen. Onto the ejector mark. The ejector mark can be a crucial part of a match when it's present on the cartridge cases. Here, it is viewed in 3 o'clock slide light, and there's also a 6 o'clock slide light view to emphasize the striations, but it can be difficult to see in 2D. I don't know if there's an expert in the room that can say this is a match. I know because I know the cartridge cases, but it's very hard to see in 2D. This is what was available currently with the Trax 3D system. But like Serge presented, we captured an accurate 3D depth, data. The black is deep, the white is high, and there's lots of shades of gray that we can't even see with our human eye that the computer can use. Some people get familiar with this type of image, and they can actually make a match with this type of view, especially when you overlap the images. Look at the comparison microscope, when you overlap them. I didn't overlap them here so you could see the full mark. But we can convert that image in the computer to show 3D, make it more natural for us, like I said before. But we can enhance it even further, such as with metallic composition. I see the match now that I didn't see in 2D before, but it's exactly the same marking that we acquired with the same equipment. We just emphasize that 3D data to help us see it. And again, this is static, but as you move it, you feel like you have a live object that is moving under the screen. And with today's growing computer power, there's countless possibilities to offer innovative viewing techniques such as this. This is the 2D comparison of matching firing pin impressions. There are similarities that we can see, but the 3D topography really tells the story. Take the time to see here. I see like a 4-leaf clover, or a flower with 4 petals. And again, this 3D model can be rendered to help see the markings, and even further enhance to bring out the surface characteristics. These viewing capabilities, they take us beyond the limitations of the conventional comparison microscope. The views obtained with IBIS Trax HD 3D, they help streamline the workflow for final confirmation on the conventional comparison microscope. And there's actually a workshop about this by my colleague, Dan. As I said earlier, these new 3D capabilities for cartridge cases are part of the upcoming release of IBIS Trax HD 3D, which contains other innovations. In addition to the new 3D correlation with its increased performance, we have also developed the correlation of the breech face sidelight image, which is already acquired by existing IBIS systems for more than 10 years. When this image is properly acquired, we can achieve even better correlation performance overall. Also integrated in IBIS Trax HD 3D is the acquisition and viewing of the bullet shape. We've been talking about this for a few years now as a prototype. And it's functional with any existing bullet track system. As was presented earlier by Danny Roberge and Rocky Edwards, this new perspective and its associated capabilities are of great value for in-depth comparisons, and especially for difficult cases. We now also have a dedicated polygonal correlation algorithm, which is almost miraculous at matching this very challenging type of rifling. Bullet shape viewing is now an integral part of matchpoint the matchpoint analysis station. Bullet strips can be compared either vertically, as is done currently, or horizontally, which can sometimes help to find a match visually. In conclusion, the main effects of IBIS Trax HD 3D are threefold. First, it increases the quality of acquisitions. It also significantly increases the level of correlation performance, especially in large data sets. And this technology gives more power to the experts during visual comparisons. Even so, Trax HD 3D is still only the latest step forward for IBIS technology, as it will inevitably bring new advancements and breakthroughs in the future. So please visit the IBIS demonstration area to see the Trax HD 3D in action. Our experts and scientists are available there to answer your questions and demonstrate this amazing technology live, because still images, although I still find them amazing, really don't show how amazing the 3D models are at visual comparisons. So thank you, and I hope you enjoy your workshops tonight.